Good afternoon, Honors Pre-Calculus. I'd like you to go ahead and write down these 2 points for the problem of the day. We have a vector with an initial point of -5, 3, a terminal point -6, 8, and so then I want you to find the component form of the vector VQ, the magnitude, the direction, and then write the vector in linear combination form. So I'll go ahead and have the sub pause the video while you complete the problem of the day, and then when the sub pushes play, we will go over the answers. Okay, here are the answers to the problem of the day. Your vector PQ should be the vector 8, 5. When we have these chevrons, that means it's in component form. Our magnitude is square root of 89. Square root of 8 squared plus 5 squared makes square root of 89. The direction angle would be 32.01 degrees. Remember, to find this, we take the tangent of our angle and we set it equal to vertical component over horizontal component. So you take the inverse tangent of 5/8 to get the 32.01 degrees. And then linear combination form means you need to write it as a sum of the I and j vectors. And so 8i plus 5j would be our linear combination form. Today we're going to continue working with section 3 of chapter 6. We're going to go a little bit further in detail with these vectors as far as how to write them, kind of working backwards a little bit. And then we're going to work on adding vectors together and do a little bit of application work. Okay, so what I want to talk about first is how we would write the component or form or linear combination form of a vector when we know the magnitude and direction. So I want to paint a little picture here for you. Here we have this yellow vector with magnitude, and theta is our direction angle. Well, we know that a vector has a horizontal component and a vertical component. So right now I want you to turn to your neighbor, and I want you to describe how you would solve for A if we knew what the direction angle was, if we knew theta, and if we knew the magnitude. How would we solve for A? Turn to your neighbor. Okay. To solve for A, we could use the cosine function. We know that the cosine of theta is adjacent over magnitude. So essentially, our horizontal component A is the same thing as multiplying the magnitude times the cosine of the angle. Similarly, we could use the sine function to help us solve for the vertical component B. We know the sine of theta would be opposite over hypotenuse. And so B, which is our vertical component, is the same thing as taking the magnitude times the sine of the angle. Now, we've worked with triangles enough. We don't have to do this every time we have a vector. What we can do instead is we can just remember that the horizontal component is the same thing as taking the magnitude times the cosine of the angle, and the vertical component is the same thing as taking the magnitude times the sine of the angle. So here's how we would write the component form of a vector given the magnitude and direction. And here is the linear combination form. I do want you to notice that cosine is associated with the horizontal component and sine is associated with the vertical component. Okay, those should go hand in hand. Also notice that if you need this hint, that alphabetical order, cosine's first, sine is second. Okay, so magnitude times the cosine of the angle gives us the horizontal component. Magnitude times the sine of the angle gives us the vertical component. Okay, so here are two examples that we are going to do. All right, our first example, we have V has a magnitude of 2 and an angle of 45 degrees. So, if we wanted to find the component form, we would need to first think about the horizontal component. The horizontal component is going to be the magnitude times the cosine of the angle. Well, we know that the cosine of 45 degrees is radical 2 over 2. So our horizontal component is radical 2. We know that to find our vertical component, we need to take the magnitude times the sine of the angle. We know that the sine of 45 degrees is also radical 2 over 2. So when we multiply that times our magnitude, our vertical component is radical 2. So our answer here, vector V is the vector radical 2, comma, radical 2. We took magnitude times the cosine of the angle to get our horizontal component, magnitude times the sine of the angle to get our vertical component. Now, our second example, we have our magnitude is 3, but we have the direction given to us as we know that it's in the same direction as negative 3i plus 4j. Okay, so first we have to determine the direction angle for negative 3i plus 4j. Which is this angle right here. Okay, so first of all, if we take the tangent of theta equals 4 over negative 3, and we go ahead and put that in our calculator as the inverse tangent of 4 over negative 3, we get negative 53.13 degrees. Now, look at our vector. Is this vector, does it have an angle of negative 53.13 degrees? No, it does not. This vector lies in the second quadrant, which means it should have an angle in the second quadrant. So instead of negative 53.13 degrees, turn to your neighbor and tell them how we would find what angle that actually is in the second quadrant. Hopefully you turned to your neighbor and said, we need to take 180 degrees and subtract 53.13 degrees. That's like our reference angle. So theta is really 126.87 degrees. So, oops, sorry guys. Come on. In order to find our vector, we're going to now need to take magnitude times the cosine of the angle for the horizontal component and magnitude times the sine of the angle for the vertical component. So what I'm going to do here is I'm going to say vector v equals, our horizontal component would be 3 times the cosine of our angle, and vertical component 3 times the sine of our angle. Kind of got squished in there, sorry about that. So in your calculator, if you take 3 times the cosine of 126.87, you should get negative 1.8. And if you take 3 times the sine of 126.8, or 0.87, you should get 2.4. So there is our vector v. In our next example, we have the magnitude and direction of 2 different angles, and we are being asked to find the sum of u and v. So first we need to write the component form of u and the component form of v, and then we can add them together. So for vector u, we have a magnitude of 4 and an angle, a direction angle of 60 degrees. So we have magnitude times the cosine of the angle for our horizontal component and magnitude times the sine of the angle for our vertical component. We know that the cosine of 60 degrees is 1/2. So 4 times 1/2 is 2. And we know the sine of 60 degrees is radical 3 over 2. So 4 times radical 3 over 2 would be 2 radical 3. I do expect that if we have any angles that are from our unit circle, you keep those exact. In our example before, we had an angle of 126.87 degrees. That was fine to punch into your calculator. But since this is a 60-degree angle and we know the exact values of the sine and cosine, I do expect you not to put them in your calculator, but give them to me exact. Okay. All right, vector v. Vector v has a magnitude of 5 and an angle of 90 degrees. So our horizontal component is going to be 5 times the cosine of 90, and our vertical component will be 5 times the sine of 90. Well, we know that the cosine of 90 degrees is 0, so 5 times 0 is 0. And the sine of 90 degrees is 1, so 5 times 1 is 5. So now, if we wanted to add these together, u plus v, we would take our horizontal components and add them together, 2 plus 0. And we would take our vertical components, 2 radical 3 and 5, and add them together. Now, since 5 is not attached to a radical 3, we cannot combine it to 2 radical 3. So our vector has to remain as 2, comma 2 radical 3 plus 5. Next, I want to talk about an application problem. So here we have forces with magnitudes of 200 newtons and 900 newtons act on a machine part at angles of 30 degrees and negative 45 degrees respectively. Find the direction and magnitude of the resultant of these forces. So we have two different vectors. Okay, our first vector that I'm going to call vector u. Our first vector has a magnitude of 2,000 newtons. Our second vector, and I'll call it vector v, has a magnitude of 900 newtons. And then it says our first direction angle, so the direction of u, is 30 degrees, while the second vector, vector v, has a direction of negative 45 degrees. So what's happening is we have two vectors, one at 30 degrees and one at negative 45 degrees, excuse my drawing. They're acting together on a machine part. And so what we care about is the resultant of these forces. So they're acting together, so what we need to do is we need to add them together and then determine what the direction and magnitude is of the sum. Okay, so we're going to have to do a little bit of work to set this up. Okay, so I'm going to go ahead and split my page all the way in half here. So we need the component forms of each of these. All right, so for u, we need to take 2,000 times the cosine of 30 for the horizontal component and 2,000 times the sine of 30 for the vertical component. Okay, now we know that the cosine of 30 is radical 3 over 2. So our horizontal component is radical 3 over 2 times 2,000. So we have 1,000 radical 3. And then we know the sine of 30 is 1/2. So times 2,000, our vertical component is 1,000. So there's vector u. Vector v, we are going to take 900 times the cosine of negative 45 degrees for our horizontal component and 900 times the sine of negative 45 degrees for our vertical component. Sorry, I kind of ran out of room there. Negative 45 degrees, the cosine of that angle is a positive radical 2 over 2. So when we multiply by 900, we get 450 radical 2. The sine of negative 45 degrees would be negative radical 2 over 2. So when we multiply that by 900, we would get negative 450. Whoop. What's going on here? Negative 450 radical 2. Okay, so here are our two vectors. What we need to do is we need to, What we need to do is find the direction and magnitude of the resultant of these forces. So we need to add these two together and then find their direction and magnitude. So when we take u plus v, our horizontal components would be 1,000 radical 3 plus 450 radical 2. We can't really add those together since the radicals are different. And then we have 1,000 plus a negative 450 radical 2 for the vertical components. Okay, now we know that we need to find the magnitude and direction of this, and these numbers really aren't nice to work with. So let's go ahead and put these into our calculators. You can do one of two things. You can take 1,000 radical 3 and add 450 radical 2. Okay. You're going to want to write down the number no matter what. But since we know that we have to use these numbers in calculations as we continue, I would either store the number in your calculator with that store feature that I taught you. Like I would store this in alpha A. Or if you're going to round, I would round to at least 4 decimal places, since we know when we get to our end result, we will round to 2. Okay, so I'm going to go ahead and write this number down and round to 4 decimal places. And then when we take 1000 minus 450 radical 2, you can either store this number in alpha B, or you can go ahead and write it down and go out to 4 decimal places. Okay, so now the magnitude of the resultant force would be the square root of a squared plus b squared. Okay, so you guys have those fancy calculators. Even if you didn't store these two numbers, those of you with an 84 can go back and pick them out of your recent, your history, and you can go ahead and take those numbers, take a squared plus b squared and take the square root of it. Okay, and the resultant force when we do this should be 2,396.19, and our label would be newtons, since that was the original forces label. Then we would need our direction. Well, we know that our direction, to find that, the tangent of theta equals the horizontal component over the vertical component. So you can either do the inverse tangent using those numbers there, or some of you are going to use either the history or the store feature in your calculator. Either way, we should get an angle of 8.73 degrees. Okay, here is our last example. It is another application. A slingshot is fired at a velocity of 30 feet per second and is fired at an angle of 20 degrees with the horizontal. We want to find the vertical and horizontal components of the velocity. So we have a slingshot, and the rock is fired at a velocity of 30 feet per second. So that is describing the magnitude of our vector. Okay, now this vector is fired at an angle of 20 degrees with the horizontal. Okay, so what we need to find are the horizontal, I'll call A horizontal, and the vertical components of that vector. Okay, well, we know to find a horizontal component, we are going to take the magnitude times the cosine of the angle. So our magnitude is 30 feet per second. Our angle is 20 degrees. So when we take 30 times the cosine of 20, we get 28.19, and it's going to have the same label as our magnitude, 28.19 feet per second. So that's the horizontal component. Okay. For our vertical component, we are going to take 30, which is our magnitude, times the sine of 20 degrees to get 10.26. Once again, our label is going to be the same as the magnitude, feet per second, and so that represents the vertical component. Okay. So throughout all of today's lesson, we basically focused on the fact that the horizontal component is the magnitude times the cosine of the direction angle, and the vertical component is the magnitude times the sine of the direction angle. What I'd like you to do for the remainder of class is get out your gold sheets and your book, and I want you to work on your assignment for the 6.3 second day. I do expect you to be working the whole time. Remember, if you do struggle with any of these problems, ask a neighbor to help you. You also could reference CalcChat for any odd problems. And I also have my homework uploaded to my website for you to see the problems that I have worked out. Okay, so go ahead and get out your books, get started, and I expect you to work until the bell rings. Have a great day.